All right, hi everyone. How are you guys doing? First of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And on this particular channel, every concept of physics, chemistry, and maths being taught to you completely in English. So this is a series that I host for class 11 students, and the topic that we are discussing today is gravitation, and this is lecture number 3 of gravitation. Hi Shiv, how are you? All right. So the subtopics that we'll be discussing covering today would be gravitational field and acceleration due to gravity. All right. So before we get started with today's lecture, let me introduce myself for those of you who might not know me yet. So my name is Rohit Dixit and I studied mechanical engineering from IIT Delhi. And for almost past 8 years, I've been teaching physics for the JEE examinations, both mains and advanced. Now, I myself was All India rank 447 and All India rank 192 in the two stages of the IIT JEE exams that I took, and I also qualified the NTC Stage 2 examination, and I was in the top 1% in the NSCP. Now, so far, all my experience of 8 years had been in offline setups, and offline, I have already guided a lot of students to top ranks in the IIT JEE examinations, both mains and advanced. And now I hope to continue doing that here with you lot online. So, as I said, before this year, all my teaching had been offline. So, this year, the new situation of COVID has forced all of us to adapt, right? So, I had to move online, and that is what you guys, you students, can also do. All right, to make sure that your preparation is going as good as it would have without the lockdown. So, what you can do is you can get yourselves the Unacademy subscription. This subscription will give you benefits like live classes. You get to interact with your educators on a regular basis. Then you have live polls and leaderboards in these classrooms, which keep them highly interactive and fun. And of course, you have test series and analysis sessions, which, trust me, is very, very important to keep tab of your performance. And also, you're starting in competition. And of course, on top of this, you have live doubt clearing sessions. So I think that's a huge, huge advantage. So for all Unacademy Plus courses, every fourth session is supposed to be a live doubt clearing session. So there, after every three teaching sessions, you can ask your teachers all your doubts related to problem solving or theories. So I think these features combined will not only make sure your studies are going ahead properly, they will even make sure that they are going better than ever. Next, your Unacademy subscription also provides you with a great never before opportunity, which is that you have now the chance to study from the topmost educators from all across India now from the comfort and safety of your home. So now you realize you may be in any part of India now. You can study from all the top educators across the country. As you know earlier, like Kota and Delhi used to be the hub of coaching industries. All the top teachers would be there. So any student would have had to go to these areas to study from them. Now you can do that from your home itself. Study from the topmost teachers of these areas from the comfort and safety of your home. All right. So, how do you get this subscription? How do you start to avail these benefits? Hi, Rajesh. How are you? So, the first step towards unlocking these benefits is to install the Unacademy app. Now, the moment you do that, you unlock yourself a lot of features. So, there are free courses which are ongoing on the Unacademy app. Okay, and then you have special classes which are absolutely free. You can attend these special classes just after you installing the app itself. You don't even need to buy the subscription to attend these. And then of course you have free quizzes. So the first step is just install the app, make use of these free features, get all this content absolutely free of cost without even having to buy the subscription. So that will give you a flavor of how your Unacademy Plus experience is going to be. Now if you think that what you see is what you like, then you can go for buying the actual subscription. And when you're ready to do that, this is what you need to do. So you can go to the plus section of the app, select your goal as IITJ, and click on that get subscription button. Then you will be redirected to the payment page where you can use the code RD Live. So there is a box here which says, do you have a code? So that is where you can input the code RD Live. This code will give you a 10% off on all your subscription fees. So hi Rajesh, how are you? And again, as I said, this is a huge, huge opportunity for you guys. You will realize that the subscription costs are already very, very competitively priced. A 12-month subscription costs around 2,800 a month, and 24-month subscription costs around 2,100 a month. So trust me, people are paying way more than this for their monthly home tuitions. So you are getting the chance to study from the topmost educators, getting the best quality content, getting the best professional guidance for your IIT JEE exam at a very, very competitive price from the comfort of your home. All right, now you can also choose from two kinds of subscriptions. So Unacademy offers you two subscriptions. One is Plus, another is Iconic. So Plus subscription is the one which unlocks all the features of Unacademy app for you. So you have complete access to all the courses that are ongoing on the Plus app. Okay, so you can take part in those, enroll in any course that you feel like, and take hold of your IIT JEE journey. Now, those of you who are looking for more guidance and more personal attention, they can go for the Iconic subscription. Also, when you click on Proceed to Pay, you will also realize that Unacademy provides you a lot of no-cost EMI options to make these payments so that you don't feel the burden of this payment. Next, let's tell you a bit about the Iconic subscription since this is something new. So a lot of students don't know much about this. So the Iconic subscription can take your JEE preparation to the next level. Why and how? So first, you will be allotted personal coaches. So that is a great feature for those of you who are not really sure, how to go about the preparation. So they will get extra help. So you will be assigned personal coaches who will closely monitor and mentor you throughout your IIT JEE journey. You will attend regular IIT JEE workshops. You'll be receiving timely guidelines. You will get a study planner, a huge deal. And of course, you will have regular test analysis sessions. So this is a program which offers you a more personalized mentorship so that again, so your JEE preparation can go to the next level with this. Okay. Moving forward, you have another chance to test your knowledge, see your standing amongst your peers, and win some of those subscriptions entirely for free in the next Unacademy Combat event. So as I said, so Unacademy is regularly hosting this Unacademy Combat, which gives you a chance to test your knowledge, get some practice, check your standing among your peers, and also a chance to win yourselves the subscriptions. So the next event is going to happen live on the 3rd of January. You can enroll now using the code RDLive. Do well in that and win yourself some cool prizes along with year-long subscriptions. Okay. So hello Amod Kumar, how are you? Good evening to you. Hi AP. Hello S Pandey. So how is everyone? Now, those of you who are following us on the YouTube channel of JEE English can connect with us on the Telegram app also using this link. So when you connect with us on the Telegram app, make sure that you are receiving all the notifications of all the lectures and sessions that are happening on this channel so that you're not missing out on any of those amazing things. Okay. Next, why don't we get started with today's discussion then? As I said, this is lecture number 3 of Gravitation. And today we'll be talking about gravitational field and acceleration due to gravity. Okay. So we started the discussion on a gravitational field in the last class, and I told you that when we tried to understand the mechanism of action of a gravitational force, so how is that force able to act from a distance? Then we came up with the idea of a field. We said that a field is something invisible that every mass will create around it, and every other mass can sense the gravitational field of this mass, and it is through fields that forces are applied. Okay, so again I told you about this. Now, if you wanted to quantify field, if you wanted to measure it, so since it is something invisible, it is something we can't see, we can't touch. So how do I measure it? The easiest way is I know one effect of the field. The one effect of field is that if there is a gravitational field at any point in space, then it can apply a force on masses present in that region, right? So if I wanted to measure the strength of the field, then easiest way is to measure the amount of force that is being applied per unit mass to standardize it. So I can now compare the fields between this point and that point by saying if I get a 1 kg mass, keep it here. If here it feels F force and if here it feels 2F force, then I can say that the field strength here is double the field strength here. So that is our standard practice of defining the gravitational field intensity, which is defined as the force experienced by a unit mass at any point in space. So you can define a mathematical value of the gravitational field strength at any point in space. Now, from that definition, you will also notice that gravitational field intensity is in fact a vector quantity. So it does not only have a direction, a magnitude, it also has a direction, right? Because the gravitational field intensity should be able to tell you not only the amount of force that a mass will feel, also the direction in which the force will be felt. Okay, so it is defined as a vector quantity. Now, gravitational field intensity, as I told you in the last class also, it's not just another, a hypothetical mathematical entity. Turns out it's a physical quantity and all masses interact with each other through fields. Gravitational fields also follow principle of superposition. Now, one very interesting thing. Turns out, gravitational fields also take finite amount of time to travel. Turns out, just like your electromagnetic fields, which we will talk about in the next class, gravitational fields actually travel at the speed of light. So that is another very interesting fact. So let's introduce you to that. Gravitational fields travel at the speed of light. What that essentially means is it brings you to a very interesting consequence. The interesting consequence is, as I said, it's the field that is exerting the force, and not the masses that are actually exerting forces. So, good evening, Motilal. How are you? The Shiv says, sir, gravitational force of Earth. That means gravity. Am I right? Absolutely. That is what we conventionally call gravity. Gravity is the gravitational force of exerted on every object by Earth. Okay. So it's just a matter of tradition. The gravitational force of Earth is called gravity. Okay. Now, as I was saying, let's talk about this interesting fact and what kind of consequence this will have. So it just means that if I had a mass present here m1, if I had a mass present here m1. So imagine if I just brought it here and you had another mass present at a distance m2. So the point is the gravitational field of this mass m1 would have taken some time to reach m2. Okay, it would have traveled with a speed of light and it would have taken some time. So if x is the distance, so time gap would have been x by c. So m2 would not have immediately felt the force due to m1. M2 would have felt the force due to M1 after a time lag of x by c. But you know, practically, the distances that we are talking about are very less, and the speed of light is huge. So you do not see that gap. Where can we see speed of light? Where can we see speed of light? So, okay, I am not sure I follow that question. Where can you see the speed of light? In what sense? So I'll give you another example. Okay, what is the interesting consequence of that? Imagine, and this was asked in a physics Olympiad. This question was asked in a physics Olympiad. They said, imagine that you have the sun, okay, you have the sun, and you have Earth rotating, revolving around the sun, right? So imagine here is our sun, and here is our small Earth, which is revolving around the sun in its typical elliptical orbit, which we talked about. And the question said, hypothetically, if the sun suddenly disappeared, what will happen to the motion of Earth? Our mobile flash have speed of light. So all light travels with the speed of light. Okay, all light travels with the speed of light, be it from your mobile flash or anything. Okay. Now, interestingly, they had asked that what will happen to the motion of Earth if the sun were to suddenly disappear. So imagine what would happen. Hi, Bharti Dasan, how are you? So this was asked in one of the physics Olympiad papers. Okay, rather astronomy Olympiad, I think, if I'm not wrong. Yes, this was asked in astronomy Olympiad. This is more relevant to astronomy. So interestingly enough, imagine that Earth is revolving in its orbit. Okay, it is revolving in its orbit. It is going with some velocity. Okay, you see it moving here. You see it moving here with some v dash. Okay, now immediately, even if I made the sun disappear, now you know why does the Earth revolve around the sun? Because of the gravitational force it experiences due to the sun, right? Now the options said if the sun suddenly disappears, then what would you think? You would have thought that it should have just moved tangentially. If the sun suddenly disappears, you would think that the Earth should have just moved tangentially and went out of its orbit, right? Now that is not the case. Interestingly enough, what happens is, see, the gravitational field emitted by the sun is going in all directions, and light takes 8 minutes to reach the Earth. So imagine just before disappearing, just at the time when the sun disappeared, the gravitational field that was coming out of the sun would have taken an extra 8 minutes to reach the earth. So for the next 8 minutes, you realize that the earth would have moved in its orbit. Okay, and then it would have gone flying tangentially. For the next 8 minutes, the earth would have moved under the influence of sun's gravity as if sun was still there. So that's a very, very interesting thing. Okay, that's a very interesting consequence of this fact that gravitational fields travel with the speed of light. Even if the sun were to disappear suddenly, that does not mean that Earth will stop experiencing its gravitational force. Turns out Earth will feel the sun's gravitational force for the next 8 minutes. And that brings me to another interesting fact that Einstein suggested. Einstein had said information can never travel faster than light. Okay. Now, what kind of information I'm talking about? So imagine if the sun disappeared. So light, takes 8 minutes to reach your eyes. So for the next 8 minutes on Earth, I should have seen that the sun is still there, right? Imagine if the gravitational field did not travel with the speed of light, and if it reached us instantly, then the Earth would have left its orbit and started to move tangentially, which would have meant that I could see the sun, but because of Earth's changed trajectory, I would have known, okay, it doesn't appear that sun is still there. So if the trajectory has stopped being elliptical, that means the sun has disappeared. Now, you would have gotten that information before that information could have been told to you by light, because the fact that sun has disappeared would have been apparent after 8 minutes. After 8 minutes, you would have stopped seeing the sun. So that is something very, very interesting, that no information in this universe can travel faster than light. So before you stop seeing the sun, you cannot stop experiencing the force of Earth's gravitational fields. Okay, so again, that makes the entire idea of gravitational fields even more important. Because as I said, it doesn't even matter if the sun is there in its position or not. As long as the gravitational field of the sun is reaching the earth, Earth would keep on experiencing the force of sun's gravitational force. Okay, so that's a very, very interesting thing to know. You won't probably find too many questions on that, but it's an interesting fact to know nonetheless. And these kind of things are asked in astronomy Olympiads. So if you're interested in that kind of thing, physics Olympiads, astronomy Olympiads, so there they do ask you such things. So again, anyways, an interesting fact to know. Okay. Now, if when I have already defined the Earth's gravitational field, let's try and calculate the gravitational field due to some common mass configurations. Okay. So first we'll be talking about gravitational field due to a single point mass. So imagine there is a single point mass kept here, and I want to calculate what kind of gravitational field it is creating at a distance r. So let's imagine I want to calculate its gravitational field as produced at a point P, which is lying here. So let's imagine that the radius position vector of this point is some r vector. So I told you the way to judge the strength of the gravitational field is to keep a mass there, a 1 kg mass. So let's keep an imaginary mass here. And okay, so just to differentiate between two masses, let's call this capital M. Okay, and let's call that mass small m. So let's imagine I kept a small m mass at a distance r. Now, from Newton's law, I could tell you what is the force that will be experienced by a small m, right? So I can say from Newton's law, I can say that F felt by m due to capital M, how much will that be? That will be minus g m over r square times r cap. Correct? It would be attractive in nature. Sir, in JEE, they will ask this question. Okay, so they just may, you never know, as a theoretical thing. but it is more likely to be asked in Olympiads. But it's just an interesting fact nonetheless. Okay, they have asked this in Olympiad. They have asked this in astronomy Olympiad. Okay, so I don't know. I don't know. JEE can ask you. It's not really that difficult a concept. It's not really something out of the blue. Okay. Anyhow. So once I know, before I know how to calculate the gravitational field intensity, and I know that I vector would be F vector over small m. So my gravitational field intensity is minus gm over r square r cap. So I realize that at any point in space, the gravitational field produced by a mass of capital M is dependent on the mass itself and inversely proportional to the square of the distance. Okay, so just like Newton's laws, the gravitational field intensity just varies. So this was our gravitational field due to a single point mass. Now let's see if I had to calculate the gravitational field intensity due to continuous masses or a system of masses. If I had a collection of masses, then what? So then I can tell you one thing, that first let's take the case of multiple masses. Okay, so instead of continuous mass, first let's say gravitational fields due to multiple masses. Okay, and then we will extend it to continuous masses. Okay, so let's imagine you had like 4 point masses. Okay, anywhere. So here is one mass, here is another mass, here is a third mass, and here is a fourth mass. So let's imagine these are different masses. Let's call them M1, M2, M3, M4. Now, what you need to do is, suppose you wanted to calculate the gravitational field intensity at a random point P. Okay, so here is again P. So let's call this vector R1 vector, this vector R2 vector, and so on. R3 vector and R4 vector. Right. Now, I know to measure the gravitational field intensity, I need to put a test mass here. So let's put a test mass here, small m. If I put a small m test mass here, then how much is the force that that mass is experiencing? That I know that we studied about this. Okay. Hello, hey, how are you? It's been a while. Okay. All right. So as I said, we already talked about this, that Newton's law of gravitation follows the principle of superposition. So the net force I know experienced by M can be calculated as this. So F experienced by M would be F experienced by M due to M1 plus F experienced by M due to M2 plus F experienced by M due to M3 and so on. Correct. So what you can say from here is that if I divide every side by this M, which is the mass of the object, then what am I getting? I'm getting that the net I at point P, the net I at point P is equal to I1 vector, I1 being the intensity, field intensity produced by M1, plus I2 vector, which is the gravitational field intensity produced by M2, plus I3 vector, which is the gravitational field intensity produced by M3, and so on. So that is what I mean to say that I can see that gravitational field also follows the principle of superposition. Field also follows superposition principle. Okay. So that's another interesting thing. Now, okay, so but sir, what will happen to density of solid is equal to density of liquid? So what do you think will happen? What do you think will happen? So that will wherever you leave it, it will float there. Okay, so imagine if you had a liquid container. You had a liquid container, and if you had a liquid in here. So if I leave such an object here, then it would have just stayed here. Okay, if I put this object here and I left it, then you realize the two forces acting on it would be mg and buoyant force, right? So it would just remain here. If I put it at top, then I would notice that it would just get submerged and float completely submerged. Okay. I hope that answers your question. If I place it gently at the top, if I gently place it at the top, then it would have become just submerged and floated here after just getting completely submerged. Okay. All right. So that is what will happen. So again, once I know that field follows the principle of superposition, I can for continuous masses also, what I can do is I can break a continuous mass distribution into a lot of point masses, calculate the field due to one point mass, and integrate that. Okay. So for continuous masses, what I can say is suppose I have a continuous mass distribution like this. So what I will do is I will break it into small point masses. So let's consider a small dm, which is a constituent of this. So a small dm. So you realize I can think of this to be made up of a lot of point masses like this, infinite point masses probably. So let's consider a 1 dm. Okay. So if I had to calculate the gravitational field intensity due to this entire thing at this point P, so what I would do is I would find 1 dm, then I would find this r vector with respect to the dm, and then the net intensity would have been I vector would have been integral of minus g dm over r square r cap. Okay, I would have just integrated that and gotten the answer. Okay. Now please remember, when I'm doing integration with vectors, I need to break it into components. Okay. So I do not integrate this directly. I would have broken that into components. Okay. So I would have said this x component of this. Okay. So okay. So let's just write that. So first let's write di vector. Di vector. I would have written the di vector. And then while integrating, I would have first broken the di vector into components because I cannot integrate vectors like that. You should remember this all the time. That I vector would have been integral of dix I cap plus integral of diy j cap plus integral of diz k cap. Now, for those of you who do not know this, that why are we first breaking it into components before integrating, is that this is a vector expression, right? This is a vector expression. Now, please remember, if I integrate this, now integration is summation, integration is actually scalar addition. In integration, you just add numbers, you do not bother about the directions. Okay. So if I just integrated this function, it would have added the different di's without bothering about their directions, which would have given me a wrong result. That is why first I break this di vector into x component, into its y component, into its z component. Now I know all the x components can be added just like numbers. All the y components can be added just like numbers, right? So then I wouldn't have had to bother. Okay, so that is the entire logic of this. Okay. So please remember this. Always break it into components. Okay, so A says float, sink, or neutral. So what do you think by neutral? So it won't sink, it would just float completely submerged. AA. It would just float completely submerged. Okay. That is something that I can tell you. All right. Now let's, with the help of that, how about if I calculate the gravitational field due to hollow and solid spheres? Now for this, we will not use integration. You can use integration, but the integration is usually long, and most of these derivations will be done in electrostatics. So we do not do all the derivations in gravitation. Okay, so please note gravitational force, gravitational force, and electrostatic force act very similarly. So what will happen is that most of my derivations, therefore most derivations are identical. Derivations and formulae are identical. are not identical, but at least similar. Because there you have Qs, here you have Ms, and things like that. Okay. So, okay. So, sir, you have also your offline coaching. I want to join. With the help of you, I can get All India rank under 100. Okay. Sure. I do not have any offline coaching yet, but I'm not sure for the future. I don't know. I don't know. I may even plan something in the future. Okay. So I don't know. Let's hope so. Let's hope, because yeah, I do miss that. So as much as I think I would love teaching online, I think I still do miss that offline study is definitely more rigorous, and at least the interaction is better. So I personally used to enjoy that, and I still miss that. So I don't know, not right now, but maybe in some future, maybe I can plan something. Okay. But you realize that will have its own limitations, right? So here you can study from me from wherever you are. So even if I had an offline setup tomorrow, let's say I'm in Delhi. So even if I started something in Delhi, how would you do that until unless you are in Delhi? Okay. So I don't know. Let's see. You never know about the future. So right now, in New Year, yes, I may plan something. Maybe when the lockdown is over or something like that. I don't know. I haven't still decided. You never know. You never know. I'm not saying no. I'm not saying yes. Okay. No commitments as such. It may or may not happen. Let's see. Let's see. There is still a lot of time. We don't know if the offline coachings are going to start anytime soon or not. So a lot of things are pretty uncertain right now. Okay, but let's see how it goes. So, what city are you placed in? In any case, what city are you placed in? Okay, so now again, for the finding the gravitational field due to a hollow sphere and solid sphere, again we will avoid integration. We will in fact use something which is called shell theorem. Okay, so let's talk about shell theorem. Hmm. This is something that Newton took a long time to prove. Okay, I will settle there if you will teach. Okay. Sure. If you know you are that passionate about this, then I think I should give this some serious thought. Okay. Definitely I will give it a serious thought. Because trust me, I do miss your offline teaching days. I do miss the interaction with students, Having to see the students. The worst part that I miss about that here is that I can't see my students. So if I can't see my students, so half the feel of teaching is gone for me. Okay, so I don't know. Let me just give it some serious thought. Okay, all right. Sure. Let me think about this. Okay, all right. So first I'll tell you about shell theorem. So again, this is something which Newton proved. We won't talk about the proof right now. Again, we will prove this also. We can prove this also in electrostatics, which we will do in class 12th. Okay. So let me just tell you quickly about shell theorem. Shell theorem says a hollow shell does not hollow uniform shell. So just a uniform also. Hollow uniform shell does not create a gravitational field at any point inside it, and for all points outside the shell, it behaves like a point mass kept at the center. Okay. So that is something interesting, which we will prove in class 12. So hi Geeta, how are you? Okay, sure, sure. Absolutely, absolutely. That is something that has been on my mind as well. Hmm. Okay. All right. So what that tells me is if I have a hollow sphere, let's say like this. So let's say I have a hollow sphere which has a mass capital M and let's say radius capital R. So let's imagine this is a hollow shell. So hollow shell is basically having all the mass at the surface only. So for any point which is lying here, so let's denote that with some other color. Any point which is lying here, so this is your R, and any point that is lying here, let's call this P and let's call that P dash. So what this theorem is telling me is that the gravitational field intensity is zero for small r less than capital R. Okay. And it also says that I vector, it would behave like a point mass kept at the center of the shell for any point outside. So for P dash, you realize it would behave like a point mass. So the gravitational field intensity would be minus gm over small r square r cap. Okay. So that is what this theorem is telling you. Now we do not define the gravitational field intensity at r equals r. Please note. Inside it's zero. Outside it's like this. At the surface, at r equals r, we do not define it because it's discontinuous. Mathematically, it's a discontinuous thing. Okay. In any case, I really don't bother about uh, the intensity at r equals r. Okay. So anyhow, so this is the definition that you have. Okay. Now for solid sphere, now the solid sphere field can be calculated very easily. Any solid sphere can be considered to be made up of a lot of hollow shells kept one over the another. Okay. So for calculating the field intensity for that, I think we have an easier approach. So first of all, I can quickly see that if I consider this is a solid sphere of mass m and a radius r. Okay, so solid sphere now. And earlier, what we considered was a hollow sphere. Okay, so for a solid sphere, what I can see is I can consider this to be made up of a lot of shells, hollow shells, just like an onion. Okay, kept one over the other. So imagine there is this shell here, and imagine there is another shell here. It is just a lot of shells kept one over the other that will make up this solid shell, right? Solid sphere. Okay. So I'll immediately realize that for any point which lies outside my solid sphere, all these shells will behave as if they were point masses kept at the center of their shells, right? So for any point which is lying outside here, let's say P, you realize that lies outside every such shell. So all such shells would start to behave as if all their mass was kept at the center. So because of that, the entire sphere would have behaved like a point mass kept at the center of the sphere. Right? So I vector would have become minus gm over small r square, where this is r, okay, r cap, or r greater than r. Now you can use equal to also here because in this kind of an expression, the left hand limit and the right hand limit converge. So the equal to sign can be considered. Okay, again, so this is your maths, limits and continuity, I hope. So here the gravitational field is continuous. Okay, so the two limits converge at the surface at r equals r. So you can apply r equals r at both. Now for a point inside, let's consider for a point inside, what do you have? So for a point which is inside, you will see something very interesting. So imagine a point P dash is lying here and this is your R. So you will realize if I consider all the shells that lie inside this. Okay, so let's consider this. So this point P just lies outside all the shells of radii R or below, right? So all those would behave as if they were all their mass was kept at the center. And how about all the shells which have got a radius greater than R? So for all those, this point is lying inside the shell. So inside, a shell does not produce any gravitational field intensity, right? and the net field intensity would be a vector sum of all those. So I can say for a point inside, okay, inside the sphere at a distance r, okay, p dash. So I can say p dash lies just outside, or lies outside all shells of radii less than r, okay, and it lies inside all shells of radii greater than small r, correct? What I will see is that it is lying just outside all the shells which are lying in this region, correct? So all these shells will behave as if all their mass was kept at the center, and this guy is lying inside all the shells lying in this region, correct? What is happening is all these shells which are lying in this region, they will not produce any gravitational field, because no shell can produce any gravitational field at a point which lies inside it. Okay. So now you have it. You can break this into two parts. One of all the shells which are lying inside, one of all the shells which are lying outside. Outside shells will not be able to produce any gravitational field. Inside shells will behave as if there were point masses kept at the center. So what will the I be? Can I say I vector would be, if the inside mass was m in, so it would be minus g times m in, all this mass kept reaches the center. Okay, so the answer would be r square r cap, right? Now, all I need to do is calculate the mass that is contained inside. I can say that the density of this is going to be m over 4 by 3 pi r cube, correct? That is the density of my sphere. So that will tell me what is the mass inside. Mass inside would be 4 by 3 pi small r cube, because that is the volume inside this into this row. Okay. What I'll realize is that this comes out to be m times r cube over capital R cube. So if I substitute this value, what I will get is interestingly minus g capital M small r over capital R cube r cap. Okay, so that's my expression for the gravitational field intensity at any point which lies inside the shell. Now I can even draw graphs, and please remember these graphs are important. JEE has asked a lot of questions on these graphs. So if I wanted to draw a graph of gravitational field intensities for a hollow sphere, let's see how those graphs would have looked like. Okay, so imagine this is your hollow sphere. Okay, and this has a radius r. And if I wanted to draw a graph of the gravitational field intensity, now let's draw this. Let's have something like this. So the gravitational field intensity, if at this, if this is x, so I'm drawing two axes, y and x. So I'm trying to see the gravitational field intensity's variation. On this axis, I will draw I, and on this axis, I have x. So what I'll notice is that the gravitational field intensity remains zero for all the points lying inside, right? So A says, answer, I never understood from 9 standard what is density. Will you please tell me in simple words? So, okay, so density by definition is mass per unit volume. Okay, how much mass is packed in a given volume. So it's a measure of that. So if you take two things, I mean, just compare. If I took something like this, and if I took something, let's say like this. So these are things of different sizes. So they may have different masses. So I want to compare how compactly the mass is packed inside these. So if I wanted to compare how compactly mass is packed inside these objects, then I compare densities. Okay. Density is mass per unit volume. Okay. So if something has higher density, that means it has, in the same volume, it has more amount of mass. Okay. For instance, if you take an iron and wood. So imagine you took balls of equal sizes, one of iron, one of wood. Which one would be heavier? The one which has more density. Okay, because that will have the more mass for the same volume. Okay. Hi Chinmay, how are you? So as I was saying, if I had to draw the graph of the gravitational field intensity, and this is how it would have looked like. From here to here, it would have been zero, from 0 to r. And for any point greater than r, it would have suddenly jumped like this, and then it would have gone like this. It would have fallen down with r square. Eventually, at infinity, it would have gone down to zero. So this is what the graph of gravitational field intensity would have looked like. Okay. Again, I am talking about the magnitude only. So please note, I am only talking about the magnitude. Sometimes they may talk about it as a vector. So when I talk of it as a vector, I may have had to draw it like this. If I draw as a vector, because it will have a minus x sign. Is this chapter gravitational? Yes. Yes, yes, I understand formula, but really I do not understand what density is. Okay, so as I said, I am trying to measure how compactly matter is packed in a material, and that is a see. Okay. So let's say why I need that. I needed density if I wanted to compare the constitution of matter in different objects. So let's say I take iron, and I take wood. Okay, so the matter is more compactly packed in one material than the other. Okay, right. So if I wanted to compare where is the matter more compactly packed, what do I do? Can I measure masses? No, mass depends on the size, right? Mass depends on the size. So if you take this much of iron and if you take this much of wood, they may have the same weight or the same mass, right? But that does not mean that the matter is uh, packed in both at the same rate. What we do is, so mass is a property that depends on the size of the object, right? It depends on the size of the object. However, density is an inherent characteristic of the material. Okay, iron, no matter what the size, will have the same density. If you take this amount of iron or you take this amount of iron, it is a property of that material, that how closely packed the matter is in that material. So if I take any amount of any size of iron, it would turns out it has a constant ratio of mass per unit volume, which is an inherent property of that material. Okay, so that is what density is. Okay, all right. In mind. Do you get it now? So this depends on material. It depends on material. It is a property of material. So it would be, this ratio would be one for iron. It would be another for wood. It would be another for let's say something like aluminum, copper. So for every material, you will realize that the ratio of mass is to volume is always constant. That is why you give it significance. See, just like your trigonometry. In your trigonometry, you realize that sine trigonometric ratios, what is that? Sine 30 is constant, which means whenever you have a right angle triangle with one side 30, you realize that the ratio of perpendicular to hypotenuse is always going to be constant as long as your angle is same. Okay, so we realize that this ratio needs to be given a special name. This is a special ratio. This is always constant. Similarly, for any material, for a particular material, the ratio of mass is to volume turns out remains constant. That is telling us about how the matter is packed in that material, and that is an inherent property of the material. Okay, and that is the significance of density. Okay, so turns out wherever you go, you take iron, you take any amount of iron. If you calculate the ratio of its mass to volume, so mass and volume you can vary. You can pick a small size, you can pick a bigger size. So you realize as you change the volume, the mass changes. But As long as you're taking iron, the ratio of masses to volume never changes. So that is why we have decided to give that a special name. Okay, that is something which is a property of the material. Same goes with wood. Same would go with copper. Same would go with aluminum. All these materials have this inherent property that for them the ratio of their masses to volume is always constant. Okay, I hope that makes it slightly clear. Okay, I don't know. Anyhow, moving forward. So let's also try to draw. Okay, please be careful here that this is the graph for magnitude, and this would be the graph if the vector was asked, if the sign of vector had to be considered. Okay, this represents magnitude. This considers sign for vector. So please remember whenever your graphs are asked, so whenever you ask questions about graphs, so make sure what they are asking. So pay attention to the language always. Now, similarly, if I had to draw this same graph for a solid sphere, then I would notice something, another interesting thing. So let's imagine if I drew this axis here and this axis here, and on one axis I wanted to represent the I, and on one axis, let's say I'm representing X. So what I'll notice is that if I look at this expression, so take a look at this expression, the field intensity actually is growing, right? You realize for different points, this G is constant, M is constant, R cube is constant. As R is increasing, this quantity is growing. So what I would have gotten is I would have gotten a straight line, turns out, a straight line up to capital R, and then it would have gone like this. Okay, so that is the kind of graph that you would have seen. Again, this is just talking about the magnitude. If you had to talk about the direction and the vector form was asked, then you would have drawn it like this. Okay, that is what you would have drawn. Okay, all right. So again, the difference between the two. I hope you understand. This is magnitude of I, and this considers direction. So if you were told that draw the diagram between the gravitational field intensity, then you would have drawn this one. If you were told draw the graph between the magnitude of intensity, then you would have drawn this graph. So pay attention to the language again. All right, so these are expressions. Again, important results. Please remember, memorize this. Important. Both these results are pretty important. So you need to memorize this. This needs to be on your fingertips. Okay. And this result is of course valid for R less than equal to capital R. At equal to R, you will realize both these equations converge. Both these equations would have given you the same result at small r equal to capital R. Okay, so important results, do memorize these. Okay. Now, why don't I try a problem with this? Okay, so let's give one problem a try. So you have been told the mass, a mass of small m is kept at a distance r from the center of a rod of mass capital M and a length capital L as shown in the figure. So you have a long rod of some mass and some length, and you have a small mass kept in front. You have to find out the gravitational force on the mass small m due to the rod. Okay. So why don't you give this a try, and let's see if you have understood what we are trying to discuss. Okay, so just give it a try. It's okay. It's the first problem, so I don't expect you guys to answer this. But I want you guys to try this first on your own before I discuss how we would approach this. Okay. So just take 2 minutes to try this, and then I'll show you how to solve this. Okay. So let's see how many of you can think about this. So I told you how to calculate the gravitational field density to do a continuous mass distribution. You want to divide the continuous mass into small point masses. Okay, that is the entire idea. Let's see. Okay, let's see if you guys can figure this out. Okay, anyone trying, by the way? So I'll wait for one more minute. If there is anyone who's trying, okay, otherwise I'll just get started. Okay, let's see. So even if you couldn't even think how to start, then don't worry about it. All right, let's go for it. What does the question say? The question says there is a rod. Okay, so let's imagine there is a rod like this, having a mass of capital M and a length of capital L. Okay, so capital M mass, capital L length, and I have to find the force that is experienced by this M, which is kept at a distance r from the center of the rod. Okay, so what I want to do is, if I can calculate the gravitational field intensity of created by this rod at this point, then all I need to do is multiply that with the mass, and then I can find out the force. So that's the entire idea of calculating the gravitational field intensities. Once you can calculate the gravitational field intensity at any point, you can find out the force on any mass kept at that point. Okay, by definition of gravitational field intensity, the force would be field intensity into mass. So let's try and calculate the field intensity that this rod is producing at that point P. Okay, let's see how we would have gone about this. So as I said, the first step is going to be I will break my mass into small point masses. So let's I can break this into all different point masses like this. Small parts. Just think that this rod is made up of a lot of small parts. Now let's consider a small part like right here. So let's consider a small part which lies at a distance x and which is spread in a thickness of dx. Okay. So first, what I want to do is I want to see the gravitational field intensity that this small point mass dm is going to create. Okay, so let's call this. So first of all, how much will this dm be? Let's try and see that. Now, can I say that dm is the mass that is spread in the length dx? Now, I can apply uh, I can apply unitary method and get it like this. Okay. So m mass is spread in a length of L. So in 1 meter length, the mass spread is m by L. So in dx amount of length, the mass spread would be m over L into dx. Okay, simple unitary method. Nothing great about this. So once I figured out the mass, now what is the distance of this mass from this point? Let's call this r dash. So if I could figure out this, then I know that the gravitational field intensity di vector would be equal to minus g dm over r dash square r dash cap. Okay. If I decide to choose my x and y like this, so all I know is that this is minus I cap. Okay. Now, since all the I is in x direction only, I don't even need to break this into any components. Okay. So I can say that I x is equal to minus g dm would become m by l dx, right? And r dash square. So can I say r dash would be r minus x? Agreed. So take a look at this expression and let me know if this makes sense. All I did was substitute all those values. So r was the distance from the center of the rod. From the center of the rod, this point is placed at a distance x away. So the distance between this point mass and point P would be r minus x. Fine. Everybody fine with this? Now all I need to do is integrate this. And the limits of x. Like x कहाँ से कहाँ vary करेगा? So the limits of x will have vary from L by 2. This would be minus L by 2. This is at this side and this would be plus L by 2. So assuming that x is considered to be positive towards the right and negative towards the left, so all I need to do is integrate this. Okay, integrate this from minus L by 2 to plus L by 2. Okay. अब ये करके देखते हैं. Let's see what that gives us. So if I just integrate this, I'll get Ix equals minus Gm over L can be considered to be constant. So taken out of the integration, right? Now integration of r minus x whole to the power of minus 2 would be r minus x to the power minus 1 over minus 1, and you would have had another minus 1 due to the minus x here. So this was the integration going from minus L by 2 to plus L by 2. Right? All these would have cancelled, and what you would have gotten is you would have gotten minus Gm over L times 1 over r minus L by 2 plus 1 over r plus L by 2. Right? Simplify that expression. Let's see what that gives us. So I can take the denominator, and then when I add, I will have 2r in the top. So I would have minus g to g over L, and here I would have had r square minus L. So this is the answer for my gravitational field intensity. Okay, now that I have calculated my gravitational field intensity, now the force is very, very simple. F due to m would be I times m, so minus 2 Gm m r over L times r square minus L square over 4. That would have been the force that the mass m would have experienced due to the rod. Now, sometimes IIT likes to do this. IIT likes to trick you. Instead of finding the gravitational force on the mass m due to the rod, they will ask, find the force experienced by rod due to small m. Okay, so they can even ask you this. So by Newton's third law, this will be the same, by the way. Okay, so it doesn't really matter whether they ask the force of by the rod, felt by the rod due to m, or felt by small m due to the rod. It's going to be the same, because you know that gravitational forces obey Newton's third law of motion. Okay, that should be simple. Now let's quickly talk about acceleration due to gravity. Now, what is acceleration due to gravity? What do we understand from acceleration due to gravity? So we know whenever a body falls under the influence of gravity alone. Now I have repeated this time and time alone. When I say gravity, gravity means the force of gravitation due to the earth. Okay. So whenever a body falls under the influence of gravity alone, the acceleration of the body is called the acceleration due to gravity. Now numerically, this acceleration is always equal to the gravitational field intensity at any point. Why? You will know that acceleration is force over mass. Now force per unit mass is also equal to the gravitational field intensity. So I can say that acceleration due to gravity in terms of the value will always be equal to the gravitational field intensity, though two have different definitions, but the formula is always going to be the same. Okay, so now gravitational acceleration does not depend on the mass of the object, but on the mass of Earth and the distance of the object from the center of the Earth. You can see that from the formula. Okay, so if r capital R is the distance, okay, between the object and the Earth, then you realize that this will be equal to mg, and this is the value of g. So if the object is placed very near to the surface of the Earth, then this is the radius of Earth. Okay, so I can say near the radius of Earth, g is equal to mass of Earth over radius of Earth whole square near Earth's surface. And this we already know has a value of 9.8 meter per second square, right? And I told you this is how Cavendish measured or estimated rather the mass of Earth. Okay, this was his entire experiment of weighing the Earth. Okay, he knew the value of G 9.8. He knew the value of radius of Earth. He also calculated from his experiment the value of capital G. The moment he could do that, he could tell us the mass of Earth. Great example of that. So now you also realize that this was already established by Galileo, by the way. Galileo had performed a lot of experiments where he threw objects from that Leaning Tower of Pisa. And what he realized is that every object, when thrown from the top, shows a single acceleration, which is 9.8 meter per second square. That value was also given by Galileo. Galileo had already proved that this acceleration is independent of the mass of the object. Okay, in daily life, when you see that not happening, the reason for that is usually air resistance. Okay, but you will, if you Google or if you find look on YouTube only, you will find a video where there is a feather and there is an iron ball which are being dropped simultaneously in vacuum so that there is no air resistance. And turns out the feather and the iron ball reach the ground exactly at the same point. So you can, if you want to see that video, you can look it up online. Okay. Now let's talk about the acceleration due to gravity. So as I said, at near the surface, the equation takes this form. So how about the variation in the acceleration due to gravity with different factors? We will first talk about g at a height h above the surface of the Earth. If I go above the surface of the Earth, then what is the value of g going to be? How is it going to change? So I know the value of g, which I will call g dash. Okay, g we usually refer to as the acceleration due to gravity at the surface itself. So g dash would be gm. Again, we are only referring to the magnitude. That's why I'm not writing the minus sign because we do not usually talk about the direction. We know direction is vertically downwards. Okay. So g mass of Earth over the total distance would become r plus h. Okay. So capital M, let's assume capital M is the mass of Earth only. I don't need to write E again and again. Where capital M equals mass of Earth and r equals radius of Earth. So this is the formula. What I realized is that if I moved above the surface of the Earth, if I went to different heights, the value of acceleration due to gravity would have reduced, and that is your practical experience also. You should know that at greater heights, the acceleration due to gravity is lesser. Okay, so the pendulums would actually have a higher time period there. Okay, they would slow down. Okay, at heights. So at on top of the Mount Everest, if you took a second pendulum, its time period would be more than 2 seconds. Again, if you don't know what second pendulum is, don't worry about it. We'll talk about that in detail. But the idea is that the acceleration due to gravity would decrease at a height. So if you drop something here, if it has some acceleration on the top of Mount Everest, if you drop this pin, you would have seen that its acceleration would have been less than 9.8. So that is something very interesting. Okay, if we can work around this equation a bit, and what we usually do is we write g dash, and I take this r common, so I can say gm over r square. Then we have 1 plus h over r whole square. Now you will realize this is the value which is g, which is the gravitational acceleration due to gravity at the surface, near the surface of the Earth. So I can say g dash is g over 1 plus h over r to the power 2. Now what we do is we also sometimes write it like this. We can write this as 1 plus h over r to the power of minus. So that is the expression for the value of acceleration due to gravity at a height h. Now, as a special case, we take another result. If h is much less than, so that just implies that h by r would be much less than 1. In such a case, I hope you know binomial approximations can be applied. So I hope you know that 1 plus x to the power n is roughly equal to 1 plus nx if x is much less than 1. Okay, so that is a binomial approximation. That is called binomial approximation. You will study that in maths if you don't already know it. Okay, so those of you who already know it, well and good. Those of you who did not know it, this is called the binomial approximation. That 1 plus x to the power n can be written as roughly 1 plus n times x if x is much less than 1. So if this is the assumption, then you realize h over r would become much less than 1. And then I can apply binomial approximation, and what I get is from here that g dash equals g times 1 minus 2h over r. This is a more commonly used result, by the way. This is what you will find in most of your books. Okay, that g at a height h is given like this. Okay, so you should remember this definitely. Okay, but you should also know how it gets to be. You should also know that this is valid only for this assumption. Do not blindly use this equation anywhere and everywhere. This equation is valid only under this assumption. Please remember. Without this assumption, this is the form. And as I said, as I keep telling you, IIT JEE Advanced likes to trick you. JEE Advanced would usually give you questions where this assumption is not true. Okay, now this is the most common formula that you memorize. The yellow one is the most commonly used formula that we use in problems again and again. So that's the one that you usually remember. And slowly, what you do is you tend to forget about the previous one, the green one. But JEE Advanced, they like to test that. That have you completely forgotten about the actual formula, and you even know that this formula is valid only under this assumption. So they will give you a situation where h much less than r will not be valid. They will tell you, for instance, if I ask you here, find the acceleration due to gravity at a height r by 2. At a height r by 2. Now, trust me, this has happened in my classes. For h equals r by 2, people apply this formula and then they say the value is coming out to be 0. So what do you mean by 0? At a height of 3200 kilometers, the acceleration due to gravity would become 0. So if I throw you from a height of 3200 kilometers above Earth, then you would just float. You will not fall. You think that. That is not the case. Trust me, don't even try that. So do not use the wrong formulae, come to wrong conclusions. And if somebody believes this, don't try and jump from a height of 3200 kilometers thinking, okay, G is 0 there, I will just float. No, that won't happen. You will fall. Okay, and you will fall hard. So that is why knowing the right formula and knowing when to use which formula is very important, because things can get dangerous if you apply the wrong formula at the wrong time. Okay. If you apply the above formula, you will realize that at h equals r by 2, in fact, the acceleration due to gravity would be, so this term you realize would become 3 by 2 to the power 2. So it would be 4 by 9 of g. Okay. So it will still be if this was around 9, so it would still be more than 4 meter per second square. Okay. So trust me, it's not like you will float. You will fall with an acceleration of roughly around 4.5 meter per second square. All right. So moving forward, let's also talk about G at a depth of d below the Earth's surface. So let's imagine this. So imagine you are digging a tunnel in the Earth, okay, and you dug a tunnel of depth d, and you want to figure out that what is the acceleration due to gravity here at a depth d. Now you realize if you take the center distance from the center to be r, then I hope you remember that the acceleration due to gravity, we just discussed it. Acceleration due to gravity would be equal to the gravitational field intensity, which was equal to gm r over r cube. Again, only magnitude we are concerned about. That's why we're not writing the minus sign and the vector sign. Okay. So this is the formula that we just calculated some time back. Now you realize what I can do is I can rewrite this as g times small r over capital R. Now, small r is nothing but capital R minus d. Okay. And small r is capital R minus d. So, if I substitute this value, what I get is g dash is d times 1 minus d by r. Now, this is the expression which has absolutely no approximations. You are right to assume that at d equals r, which means if I reach the center of the earth, then yes, g is 0 and you would have floated. So if you could reach the center of the earth and then you could jump in the air and you would have actually floated. Okay. However, if you could just survive the heat of the core, if you don't just vaporize first before reaching reaching the core of the earth, yes, you could have dug your way to the center of the earth, jumped out there, and you would have been floating. Okay, just like in free space. So yes, this is another important formula that you must remember. And the good part about this is absolutely no assumptions here. Okay, so this is always valid. We do not make any assumptions before getting this formula. Okay, so this is valid. This is true. Even for a depth equal to r, it is true. Okay. Hello, nothing peace. How are you? All right. Next, there are two more factors which cause variations in the values of g. One is the change in value of g due to the shape of the earth. Now, those of you who don't know this, let me tell you that earth is not a perfect sphere. In fact, earth is a shape that we call geoid. Shape of the earth is geoid. For those of you who have studied geography, would know this. Call this shape geoid. Okay, so it bulges at the center. So what you realize is that it is if you imagine, if you have a tennis ball, okay, if you rotate that very fast, what will happen due to the centrifugal force? It bulges from the center. So that is what the shape of Earth looks like. Now, because of that, what you realize is that the radius of Earth at equator is higher, and the radius of Earth at the poles is lower. What you realize is radius at poles is less than radius at equator, and you realize since G is equal to capital G, capital M over R square, and G is inversely proportional to R. So what does that tell you? That tells you G at poles is greater than G at equator. Now you may have heard about this. You should know about this. The acceleration due to gravity at poles is higher than the acceleration due to gravity at the equator. Okay, remember that. Now there is yet another factor affecting the value of G over the surface of the earth. So first we went above the surface of the earth, then we went below the surface of the earth, then we were moving along the surface of the earth. So along the surface of the earth, as you move from the equator to the poles, the value of G increases, right? Another factor, one factor was the shape of the earth, the not so spherical shape of the earth. Another factor for that variation is the rotation of the earth. Now, because of rotation of the earth, what happens is, imagine if you have anything which is kept here, that object would have felt a centrifugal force. Okay, so any object kept over here is actually rotating with the omega of the Earth, and it is rotating in a radius of small r. So it will feel an outward force, which is the centrifugal force, right? Now, if this place has an angle phi, then I can divide this into two components, this and this. So this is phi. So I can say that the component of the centrifugal force vertically that it would feel is m omega square r cos phi. Correct. So the effective force of gravity that this body will experience is, I can say that F net would be the mg minus m omega square r cos phi. Okay, I hope you can realize that this is the net force that the body will be experiencing at the surface. Okay. Now, if I can say because of this, if I say that what I will feel is that the value of G has changed. So F net can be written as M times G dash, where G dash is the, or G effective, I can say G effective is the effective value of acceleration due to gravity. So I can replace that, and what I'm getting is this, right? If I get moved, so the expression that I'm getting is G effective at any latitude phi would be G minus omega square R cos of. Now let's try and figure out what R is. We realize this is the capital R, the radius of Earth, and this is small r. So from this triangle, I can see that small r is nothing but capital R cos phi. Okay, so I can also say that also small r is capital R cos of phi. If I substitute that value, then what I get is G effective, in fact, equal to G minus omega square R cos square phi. Again, that is an important result that you must remember. Now, due to the rotation, the effective value of G, again you will realize, would be minimum at the equator, because at the equator the phi is 0 and at the poles the phi is 90. So you realize the reduction in the effective value of gravity due to rotation of the earth is maximum at the equator and minimum at the poles. So due to the last factor and this factor, you realize G at poles is the highest. If you go anywhere on earth, therefore G at poles equals highest and G at equator is lowest. In fact, I remember the first time as a student that I studied this. So I thought it would be a good business plan if I could, buy gold at equator and sell it on poles, right? Just because of the variation of G, maybe I will make profit. Then I realized when they measure gold, they measure it by that balance, where it wouldn't matter, right? Only if it was bought in spring balance, then it would have mattered. So my business idea turns out did not do that well. Okay. But yeah, that was an interesting business idea as a kid that I had. Now another interesting thing is if you're living over here and you want to lose weight, then you can go to equator. On equator, because the value of G is lesser. So when you're standing over the weighing machine, you would have lost some weight. Okay. So even if suppose especially from the cold countries which are near the poles, the variation of G can be around zero point 0.5 meter per second. So if that is the kind of variation, if the value of G reduces by zero point 0.5 meter per second, so that's a significant change. I think that's a 0.1% change. So a person like me may feel happier when I weigh myself on equator. So that is another interesting thing that you can do. Okay, now why don't we try this problem and then we will wrap up today's session. Okay. So this again is a question that has been asked in a JEE Mains a lot of times. I think they have asked in advance also. So I can tell you that this is a mains. Oh, I has been asked, in fact, more than once. More than one. I told you, JEE Mains people like repeating their questions. So let's see. The question says, suppose the Earth increases its speed of rotation. At what new time period will the weight of a body on the equator become zero? Okay. Take G as 10 SI units and the radius of Earth as 6,400 kilometers. So give this a quick try and then we'll wrap up today's session. Okay. So remember the formula. Why? How does the gravity reduce? The gravity was getting reduced due to the centrifugal force by this equation. All you need to do is, if the G effective becomes zero, if the effective value of G becomes zero, then the weight of that body would be zero. And in fact, you will realize not weight of that body, weight of any body would be zero. So any body that you would take the weight at the equator, if Earth was spinning faster enough, if the Earth was spinning faster enough, then the centrifugal force at the equator would be so high that it could counter your attraction due to gravity, and everything on equator would have felt a zero amount of gravity. So you would have just floated maybe at the equator. You would have felt lighter, so to say. Okay. So how do I calculate this? So let's just quickly do this because we are running out of time. So I know G effective is the G minus omega r cos square phi. Now at equator, what is the value of phi? Phi is 0, so I can say, and we want the effective to be 0, so therefore omega should be root of by r. Your answer. Now, if I can find the omega, you can find the time period. So time period of the day would be 2 pi over omega. Okay, so let's see. Time period would be 2 pi root of 6400 over. So 6400, I think 64 is 8 square and 100 10 square, so 80. And G I can roughly take as 10, which is roughly around pi square. So I can say G is roughly around pi square. So what I can do is 2 pi into 80 over pi. So time period would be 160 seconds. So if your duration of one day became 160 seconds, that is slightly more than 2.5 minutes. If the Earth started spinning that fast, then the effective value of acceleration due to gravity at the equator would have become 0. Okay, so that is your answers. Okay. Now with that, let's wrap up today's discussion. We will talk about more problems in the next session. Okay. All right. That is our time for today. But before I leave you, please let me remind you that if you haven't gotten your Unacademy subscriptions, what are you guys waiting for? So there is absolutely no time to waste for a competitive exam like JEE. Okay. So go get your subscriptions as soon as possible, and this is how you do it. Go to the plus section of the app. You select the goal as IIT JEE. Click on that get subscription button. Okay. When you're redirected to the payment page, two very important things. Do not forget to use the code RD Live. This will give you a 10% off. And then when you click on proceed to pay, you can select a no cost EMI option for you to use that payment fee. Now you can also select from these two kinds of subscriptions, plus or iconic. Talking about the iconic subscription, this subscription gives you a more personalized guidance for your JEE journey. This will take your JEE preparation to the next level. You will be allotted personal coaches. Then you will be attending a lot of IIT JEE workshops, receiving expert guidelines from time to time, getting a study planner, and having a regular test analysis sessions. Okay. Next, don't forget to take part in the next Unacademy Combat event, which is going to happen live on the 3rd of January. Okay, use the code RD Life, take part in that, do well, and you can win yourself some really cool prizes and rewards, which include up to 1 year subscription of the Unacademy plus extra rewards. Okay. Now, if you like today's video, then don't forget to press the like button and share it with as many people as you can. As I keep saying, this is absolutely great quality content being provided to you completely free of cost, just to make sure that all those students who can't afford these subscriptions should also get access to quality content, quality education. Okay, so make sure that happens. Play your role. Okay, share the video, spread the love. Okay, and if you're new to this channel, don't forget to subscribe to the channel to keep on getting access to all this quality content. Don't forget to press the bell icon, and the PDF of all of the slides used in today's lecture would be available for download soon. For those of you following us on the Telegram app can join us. Oh, sorry, those of you who are following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link, so that again you are receiving all the timely notifications. Because a lot of times people miss getting notifications from the YouTube app. Okay, so make sure you are there on this group so that you know about all the sessions and lectures happening on the JEE English channel. So that is it. That is my time for today, guys. And this is where I would like to wrap it up. And before I leave you, let me remind you, this is my code RD Life. Use this code, get your next Unacademy subscriptions, and enjoy a 10% off. So I'll see you next day after tomorrow, where we will carry forward this discussion that we're leaving today. Okay, till then, you guys keep studying hard, keep practicing, and take good care.